Dear students, welcome to the lecture series on the topic Engineering Graphics. So today we are going to continue with our earlier discussion on the topic Projections of the Oblique Lines. So I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now we have already discussed about the oblique lines. So the oblique line is the one which is inclined to both horizontal plane as well as the vertical plane. So an oblique line, it is a straight line that is neither horizontal nor vertical. So since an oblique line is inclined to both the horizontal and vertical planes, its projections on HP and VP will reveal its apparent lengths, and neither of the front view or the top view, they will be parallel to the XY reference lines, and we are not also going to get the true length of the lines in front view as well as in the top view. And since an oblique line, it is inclined to both horizontal plane and the vertical plane, it will have both the horizontal trace as well as the vertical trace, and these traces, they will be drawn through the projection lines, that is A dash, B dash and AB respectively. Now a little bit of recap of whatever we have already discussed. So the projections of the oblique line, they are drawn based upon the fact that this line is inclined to both HP and VP. So here you can see this is the spatial representation of an oblique line where the distances of the ends A as well as ends B and B, they are different from HP and VP, and since the coordinate distances of the end A as well as of the end B, they are different from HP and VP, so the projections, they will be not parallel to the XY reference line, they will be always inclined to the XY reference line. So this is the basic indication that the line that we are going to talk about, it is an oblique line. So these are the projections of an oblique line. Now this line is oblique because the distances from HP and VP for the two ends, that is A and B, they are not equal to each other. Similarly over here also the distances of the plan from the vertical plane, they are also not equal. So that is why you get the inclined apparent length in the front view and the inclined apparent length in the top view. So the angle of inclination of the front view with the horizontal plane or the XY line, it is called alpha, and the angle of inclination of the apparent length in plan with respect to VP or the XY line, this is called angle beta over there. Now this is again recap, that is we know the basics that how do we obtain the projections of the oblique line. Now we need to remember the basics over here, that whenever you have a line which is parallel to the vertical plane, its projection in the front view on the vertical plane will provide you with the true length of a line. So these basic fundamentals we are going to apply while we work out the projections of the oblique line. So here you can see we have a line which is inclined to HP and it is parallel to the vertical plane, and since the line happens to be parallel to vertical plane, you can see this line, it is parallel to the vertical plane, so the true length will be available in the front view on the vertical plane. So we need to remember that whenever the apparent length of the line, it is parallel to the vertical plane, so on the vertical plane we are going to get the true length of the straight line. Similarly the vice versa, whenever the line is inclined to the horizontal plane and it is inclined to the vertical plane and it is parallel to the horizontal plane, so its true length will be observed on the horizontal plane in the top view. So here you can once again see this is a line which is parallel to the horizontal plane over here. So the front view projections are shown over here, and this is a line which is inclined to your vertical plane. So please check this out. This is a line which is inclined to the vertical plane, but it is parallel to the horizontal plane, so its true length will be observed on the horizontal plane in the top view. And here you can check these projections, that is projections of the front view, they are parallel to the XY reference line over here. So this way we conclude over here that whenever the projections of the line, they are parallel to the horizontal plane, so obviously the true length will be obtained in the opposite view, that is on the horizontal plane in the top view. So these two corollaries we have already used. Again a little bit recap regarding how did we obtain the projections of the oblique line when both the ends of the line, they happen to be lying in the first quadrant. Because today we are going to pick up with a problem where end A of the line happens to lie in quadrant number 1 and end B of the line happens to lie in quadrant number 3. So there the same fundamentals of this case we are going to apply. So please check this out. So in the first case that we discussed in the earlier lecture deliberation, so we had worked out that this is a line A dash B dash in which the coordinates of end A, they were provided to us, that is coordinates of end A were 10 mm in front of VP and 20 mm above HP. Similarly, the distance between the end projectors was provided to us as 50 mm. End B happened to be 50 mm above the horizontal plane and 55 mm in front of the vertical plane. Now in this case, since the line is an oblique line, so we observed that none of the apparent lengths, they were parallel to either HP or the vertical plane. So since the name of this method is rotation of line method, so what we did, we rotated one of the apparent lengths to begin with and made it to get parallel to either horizontal plane or the vertical plane. So here you can see we are using this basic fundamental that we just discussed a little while ago. So here you can see whenever the apparent length of the line happens to be parallel to the horizontal plane, its projection on the horizontal plane, that is in the top view, will provide us the true length of the line and the true inclination angle with the vertical plane. So here you can see we are going to use the rotation of the line method. So here my needle point will be there. So the 4 locus lines we have to draw because we have to rotate the lines and draw the perpendicular projections from there. So please see, here will be my needle point. My compass pencil point will be this one. I am going to rotate this apparent length so as to make this apparent length remain parallel to the horizontal plane. The moment I rotate this, since I am rotating the elevation point, projection point, so the new point available will be B1 dash. And now A dash, B1 dash, just like this. This projection becomes parallel to the horizontal plane. Now once I get an apparent length projection parallel to the horizontal plane, I am going to draw a vertical projector over here and my true length will be appearing over here. Now the question arises, how much I need to draw this perpendicular projector? I need to draw the perpendicular projector from B1 dash till the locus line of the second end point of the plan projection over here. So please see, I'm going to drop a perpendicular onto the locus line of point B. So since this projection was B1 dash, so the point obtained over here will be B1. If this is B dash, this will be B. If this point's name is B1 dash, I am going to get B1 over here. So this is going to give me my true length. So I mark this point and then join AB1. And this AB1 will be my true length of the line. And once I get AB1, so obviously I can mark the angle phi over here, that is the angle of inclination of this true length with the vertical plane. Now similarly, now I am going to rotate this from the other side. Now I'll use this fundamental whenever my apparent length happens to be parallel to the vertical plane. So once I get this projection parallel to the vertical plane, I get the true length of the line on the vertical plane in the front view, that is A dash B dash. So now again you see I am going to have my needle point over here. This will be my locus line. Now up to this locus line I need to draw this arc. So keep your compass needle over here, open compass this much, draw an arc. And since this is the second rotation, so I will mark this rotation as second one. So it will be B2. So once I get this B2, what do I get? My apparent length, now I have make it parallel to the vertical plane. Now once I make my apparent length parallel to the vertical plane after the rotation, a vertical projection I need to make towards the B point, that is B dash locus line point. And once I reach here from this particular projection B2, so I will be getting my B2 dash point over here, which is going to give me my true length of the line in the front view. So then I am going to join this A dash B2 dash, and once I join this, because this is an inclined line, I am going to get angle theta. So angle theta is the angle of inclination of the true length in elevation with the horizontal plane. So angle theta is obtained. After obtaining both true lengths, now my self check is that the first true length has to be equal to the second true length, that is A dash B2 dash has to be equal to AB1. If both the true lengths they happen to be equal, it means I have made the appropriate rotation. Otherwise I need to check, maybe either I have rotated it more, that is I have exceeded the locus line presentation over here. So I need not exceed this rotation beyond the locus line of the end A dash as well as of the end A. Now having obtained the true lengths, now I am going to mark angle alpha, that is for the existing apparent length of the line in elevation, that is alpha is the angle of inclination of projection A dash B dash in the front view with the horizontal plane. Similarly angle beta, it is the angle of inclination of the projection in plan with the vertical plane over here. Now I need to draw the traces. Now A dash B dash, once I extend, that is my projection line, not the true length. So these black lines I need to extend. So once I extend this, wherever this extension meets the XY line, so I get the point H dash. Now from here I am going to draw a vertical line and see where this vertical line meets the extension of the plan projection length. So I am going to now extend my plan projection line over here, that is AB, and the top portion wherever it meets the vertical projector, this intersection point will give me the point H. Now I am going to measure this H dash. I will be getting the value of my horizontal trace. Similarly I need to work upon the vertical trace. In order to work out the vertical trace, I have already extended my plan projection line, that is AB. Wherever this plan projection line is extended and it meets my XY line, I am going to mark this point as point V, that is the base of my vertical trace, and then I will again draw a vertical projection from here and see to it that wherever this vertical projection meets my elevation projection line A dash B dash, it may meet above the XY line or it may meet below the XY line. So I need to draw this vertical projector on either side. So over here, because this A dash B dash projection line is passing like this, it is going to meet this projection line above the XY line. So again I am going to measure this distance and I will be getting the vertical trace of the line. So this is the recap of whatever we have already done. So we need to remember true lengths A dash B2 dash and AB1, they should be equal. So angle theta, it is the angle of the true length in elevation. Angle phi, it is the inclination of the true length in the plan. Angle alpha, it is the inclination of the apparent length in the elevation. Angle beta, it is the inclination of the plan projection length with the vertical plane. And please check, alpha is greater than theta and beta is greater than phi, and similarly true lengths, they are greater than the apparent lengths over here. And another thing we need to remember, angles theta and alpha, they are drawn through A dash. Angles beta and phi, they are drawn through A. And very important, apparent length projections A dash, B dash and AB, they are always rotated. And then they are made horizontal first of all after the rotation, and they are further extended to obtain the true lengths over there. Mind you, true lengths, they are never extended. Apparent lengths, they are always extended. So please see, apparent lengths, they are first of all rotated and then they are extended to give you or provide you with the true length of a line. So HT and VT, they are obtained after extending A dash, B dash and AB. So this is the recap of whatever we have already done. We have just discussed this particular case because now we are going to enter into more complex case. That is, in this case, point A and point B, both of these points happen to lie in quadrant number 1. Now we are going to pick up another case where point A or the first point of the line will be lying in the first quadrant, while the second point of the line will be lying in the third quadrant. So let us see how do we draw the projections of those lines or those oblique lines. So this is over here case number 1 once again, regarding those lines where first point is lying in the first quadrant while the second point of the line is lying in the third quadrant. That is, the orientation of the line is changing. And once the orientation of the line is changing, so obviously it may create little bit difficulty for you to have proper visualization of the rotations over there. So that is why we need to remember the basics, and once we remember the basics, we will be able to attempt these problems with ease over there. So once again, since it is case 1, so the coordinate positions or locations of the ends A and B or E and F, they will be provided. First and second point, they will be provided, and the distances between the end projector, they will also be provided. And once these two things they are provided, we'll be able to draw the projections of the line first of all, and then again we'll follow the same route, that is, rotate the projection A dash, B dash or E dash, F dash and EF to make it parallel to HP and VP, and then draw vertical perpendicular lines to the second point of the opposite side, so that you get or you obtain the true length of the line in front view or in the top view. So we need to work out the true length of the line in both front view as well as in the top view. We need to determine the angles of inclinations of these two lines with HP and VP, that is angle theta and phi will be worked out, and again the traces of the line, they will also be worked out, and the method used, again it will be the rotation of the line method. So let us read out the problem over here. The projectors through the ends E and F, they are 60 millimeter apart. So you know the distance between projectors of E and F, that is two ends of the line. The distance between the projectors, they have been provided. End E, it lies 15 millimeter above the horizontal plane and 20 millimeter in front of VP. So this point happens to lie in quadrant number 1. That is, end E means that E dash will be drawn 15 millimeter above the XY line, and E, the projection E will be drawn, that is the top view of the end E will be drawn 20 millimeter below the XY line. Similarly, end F is 10 millimeter below horizontal plane and it is 35 millimeter behind the vertical plane. So since this point F lies 10 mm below HP and 35 mm behind VP, so this point lies in the quadrant number 3. So in quadrant number 3, my front view, that is 10 mm below HP, that is my F dash point, that is front view F dash, will lie 10 mm below XY, and my top view, that is 35 mm behind VP, means the F point projection, that is plan projection for the point F, will lie 35 mm above the XY line. So once the projections they are known, I need to work out the true length of the line, the traces, the inclinations of the line with HP and VP using rotation of the line method. So let us first of all draw the projections. So this is again case 1, when the projections are given, true length, theta, phi and traces, they are to be evaluated. So please check this out. Let us draw the projections of the end E. So end E is 15 mm above HP and 20 mm in front of VP. So E dash will lie 15 mm above XY line, and end E will lie 20 mm below the XY line. So these are the projections of the end E, which is lying in my quadrant number 1. Now the distance between the end projectors of E and F, they are 60 mm apart. So now I'll draw another vertical projector line where the projections of my end F will be lying, and two projections, that is projections of E and F, they are 60 mm apart. Now let us draw the projections of the end F. So where does those projection they are going to lie? Now end F is 10 millimeter below HP. Now 10 millimeter below HP means this will be my front view. 10 mm below HP will be my front view. I'll mark point F dash over here. So please see, I am going to mark point F dash. Similarly, point F is 35 mm behind VP. So 35 mm behind VP will mean that it will lie above the XY line. So please make sure once you mark these points E dash, F dash, E and F, many students they'll make the mistake that they will be joining these 2 points and they may write F dash and F over here. No, point F lies in third quadrant. So whatever is the distance below HP will give you your front view, that is F dash. Whatever is the distance behind VP, it will be drawn above the XY line because the point happens to lie in quadrant number 3. In quadrant 3, plan lies above the XY line, front view lies below the XY line. Whereas in quadrant number 1, front view lies above the XY line and the top view lies below the XY line. And once I have marked these 2 points over here, that is E dash and E, F dash and F, very carefully and meticulously I need to join E dash with F dash and E with F over here. Having drawn the projections, now one thing I need to do, I have to draw the long locus lines from E dash and F dash in the front view. Similarly, I need to draw long locus lines from E and F over here. So please see, 4 locus lines I need to draw. First one, E dash and F dash. Second one, E and F. So after drawing the 4 locus lines, now I need to recall, because now it might seem to be confusing, but it is very easy if I remember the fundamentals. What are my fundamentals? Both in the front view as well as in the top view, I have to make one rotation. Why rotation? Because I have been provided with the projection, and these rotations will be, you can rotate your front view to make it parallel to the HP. Just see, I may rotate my front view to make it parallel to VP, and then from here I'll draw a perpendicular projector onto the plan view over here. So this will give me my true length point over here. Similarly, this is my plan projection. So what I can do, I will pick up my needle over here and pencil will be here. I will be rotating this apparent length. This is my apparent length. And once I rotate this apparent length, you see 1, 2, 3 barriers, they are in between. I need not bother about these barriers because I know it very well. I have to make this apparent length parallel to the vertical plane, and it will become parallel to the vertical plane once I rotate this particular distance or the projection length at the locus line of my needle point over here. So I'll start my needle over here, pencil will be over here, I'll be rotating it till it becomes parallel to VP. Similarly, over here, this is one barrier. No, don't be obstructed by that. This is my needle point. My fundamentals are clear. I will open my compass this much, rotate this line, make it parallel to the horizontal plane. So this is very, very easy. But for that, I need to remember this fundamental. So always keep this particular fundamental in your mind, and I know it very well because earlier it used to be on only on one side I was making a rotation and then drawing the perpendicular projection onto the other side. But once my fundamentals are clear, I know that whenever I make a rotation, I'll make my apparent length parallel to either HP, or I will rotate my projection and make it parallel to VP. That is the only thing I need to remember. Then from there, draw perpendicular projection onto the second point of the opposite view. I'll get my true length. So let us start over here using the same fundamental. So that is why we had a recap of this particular case. Otherwise, we would have straight away started with this question. No. So over here, E dash, F dash is my front view projection line. I'll keep my needle of the compass over here. This is my locus line. That is why I have drawn a long locus line over here. So open the compass this much, rotate it, rotate the apparent length, make this apparent length parallel to the horizontal plane. So just see, this rotation goes like this, whereas in the first case we were rotating it like this. So it is the only change in this question compared to this question is orientation of the projection. Otherwise rest of the things, they remain the same. So please check once again. I repeat, E dash is my needle point. Open the compass this much, rotate this projection so as to make this projection E dash F dash parallel to HP. So since I have rotated this first, so my first rotation means that F dash gets converted to F1 dash. So having obtained this apparent length parallel to the horizontal plane, now I need to draw perpendicular towards point F, that is second point of the opposite view. So from here I am going to draw a projector line, and mind you, please see, both the arrows have to be marked over here, indicating that the projection has been rotated first and then the vertical extension has been made over here. So after making this vertical extension, after getting your apparent length parallel to the horizontal plane, I get this point F1. So F1 dash and F1, they will fall in one vertical line. And the moment I obtain this F1, I have obtained the second point of my true length in the plan. Because the line was, we have already discussed that whenever my apparent length happens to be parallel to the horizontal plane, on horizontal plane in the top view, I am going to obtain the true length of a line. So you see, in the top view I have obtained this point F1, and I am going to join E with F1. So black one is the given information, blue one is the information which has been derived. Now second rotation, now let us rotate it. I'll keep my needle over here, E. Now as I told you earlier, intermediate barrier 1, 2, 3, least bothered about these three. Why? I know a simple fundamental that my plan projection line is inclined. I want to make this inclined plan projection line parallel to the vertical plane, and when it will become parallel, when I am rotating this point F up to the locus line of end E. So this is the long locus line of end E which I have drawn with 2H. So I'll open my compass this much. This is not going to distract me. This is not going to distract me. This is not going to distract me, because if I end up over here, my line will not, my projection in plan will not get parallel to the vertical plane. So I am focused about making this apparent length, that is EF, parallel to VP. So please see, here also I did the same thing. I rotated it, made it parallel to VP. Over here, since the orientation of the line has changed, so I am forced to rotate it like this. So here I obtain this second point F2. Having obtained this F2, now my apparent length in plan becomes parallel to the vertical plane. Now what I need to do, I need to draw the perpendicular projection onto the elevation locus line, that is elevation locus line of F dash. So from here F2, I will be drawing a perpendicular from F2 to cut the locus line to intersect with the locus line of the F dash point of the elevation. Because we have already discussed this, whenever my apparent length happens to be parallel to VP, my true length will be available on vertical plane in the front view. So you see, in the front view E dash, F2 dash I have obtained. So true length in the elevation, true length in the plan I have obtained. So having obtained these true lengths, now self check has to be applied that the true length EF1 must be equal to true length E dash F2 dash. So if these true lengths they don't turn out to be equal, it means we have made some mistake regarding the rotation, that is while making the line parallels over there. Otherwise there is no chance that some error will be creeping in. So having worked out that this length E dash F2 dash is equal to EF1, I am very much sure that I have attempted this question properly. And then I want to mark the angle theta. So angle theta is the angle of inclination of the true length of the line in elevation or in the front view with the horizontal plane. So this angle you need to measure and mark it onto the drawing. Similarly, angle phi, that is the angle of inclination of the true length of the line in plan with respect to the vertical plane. So both these angles theta and phi we have evaluated and we have marked it onto the drawing over here. Now please check, in the earlier cases you see we had to extend our projection lines A dash, B dash and AB to obtain the traces over there. Why? Because these projection lines A dash, B dash and AB, they were never intersecting with the XY line over here. But you can check the black lines, E dash, F dash is itself intersecting with my XY line. Similarly, E and F is itself intersecting with my XY line. So I don't need to extend E dash, F dash and EF to obtain the horizontal and vertical traces. Now since both of them they are intersecting, you see wherever EF intersects with XY, this point's name will be V. From here you draw the perpendicular onto the elevation projection line. This will give you V dash. So this is V, this is V dash. Similarly, wherever my E dash, F dash is intersecting my XY line, this point will be H dash. Now from here you draw the vertically perpendicular upward. So wherever it intersects with the plan projection line EF, this point will give me the second point over here. So this way, please check this out. So this is elevation. Once again I repeat, this is elevation, sorry, this will be H dash over here, this point will be H. Similarly, this is EF, wherever it intersects this XY line, this point's name will be V. So here V dash will be obtained over here. So please check, V lies here because EF is intersecting with XY gives me V, and at the top of it where the vertical projector intersects the elevation projection line, this gives me the point V dash. Similarly, where E dash, F dash is intersecting my XY line, I obtain point H dash over here. And then you take perpendicular distance above or below, wherever it intersects with the plan projection line, you get the point H. So measure the vertical trace distance, measure the horizontal trace distance, and you can write it onto your drawing sheet. So once again, all the other fundamentals they remain same. That is, first true length, that is E dash, F2 dash must be equal to second true length, that is EF1. Angle theta is the angle of inclination of true length with the horizontal plane. Angle phi, it is the angle of inclination of the true length in plan. Alpha and beta, they will be greater than theta and phi. And very important thing, apparent length projections, that is E dash, F dash and EF, they are always rotated and made horizontal, and they are further extended to locate the true length. So same thing which we had discussed earlier on, and true length happens to be greater than the apparent lengths in both elevation as well as the plan. So these are the projections of an oblique line in which the first point happens to lie in quadrant 1 and the second point happens to lie in quadrant 3. So over here the projection lines need not be extended to get the or obtain the traces of the line, because the lines themselves, they are intersecting with your XY reference line. So let us now work out another case, that is case number 2 of the same nature, that is first point lies in the first quadrant while the second point lies in the third quadrant. But in this case we call it case 2 because here the true length is given, angle of inclinations with HP and VP are given, and we are required to work out the projections of the line. That is, the arrows have to be reversed regarding the case 1. So let us read out the statement. A line AB which is 100 millimeter long has one end A 50 millimeter above HP and 50 millimeter in front of VP, and A lies in first quadrant, and the front view, that is A dash, will be drawn 50 millimeter above the XY line, and the top view of the end A will be drawn 50 millimeter below the XY line because the point lies in quadrant number 1. Its midpoint is 15 millimeter above HP and 20 millimeter in front of VP. You see, we haven't provided you with the coordinates of end B. So total length is given 100. So the midpoint will be at 50 millimeter. So that particular midpoint should lie 15 millimeter above horizontal plane and 20 millimeter in front of the vertical plane. So we will be drawing the projections of the line. So true length is given. From true length, now we need to work out or evaluate the projections, the angles of inclination, that is alpha and beta with HP and VP, and we are also required to work out the traces of the line, again using the rotation of the line method. So please check this out. Let us draw whatever original data is given. So please see the coordinate locations of end A we have drawn. A dash lies 50 millimeter above HP because this end lies 50 mm above HP. So this will lie, A dash will lie 50 millimeter above the XY line, and end A is 50 millimeter in front of VP. So here 50 millimeter above and 50 meter below XY, I have drawn A dash and A. Next, the locus line for the midpoint in front view lies 15 millimeter above my XY line, above HP. And for the plan, the locus line of the midpoint, it lies 20 millimeter in front of VP. So 20 millimeter in front of VP means it will lie below the XY line. So the midpoint of M dash lies 15 millimeter above the XY line, and for the plan, the midpoint lies 20 millimeter in front of VP. So we have located the midpoints over here in front view as well as in the top view. We know the true length of a line, that is 100. So if this is midpoint, so I'll open my compass 50 millimeter and further extend it by another 50 millimeter so that the true length of the line will become 100. Similarly, from here as well, I'll keep the needle of the compass here, mark an arc 50 millimeter, and then extend this line another 50 millimeter so that I get the true length of the line 100. While this will serve as this locus will serve as the midpoint of the true length of the line. So let us do that. So please see, true length is 100. So I have marked 50 millimeter first of all because this is the locus of the midpoint. So this is first 50 millimeter. Extend this further by another 50 millimeter. So 50 plus 50, that makes it 100. So this is my true length of the line. I marked this A dash. I can't write B dash over here. So true length has to be marked by B1 dash or B2 dash. So I have marked it as B1 dash. So again I have drawn a locus line. You see, first long locus line I have drawn from A dash. Second long locus line I have drawn from A. Then having obtained B1 dash, again I have drawn a long locus line. Similarly, from the plan again I need to draw the plan projection for the true length. So please check, this is my coordinate location, that is starting point. I'll open my compass 50 millimeter because true length is 100 once again. Again extend this 50 by another 50 So this 50 plus this 50 makes it 100. The moment I obtain the second point of the true length, which is 100 millimeter, again I'll draw a long locus line over here using 2H pencil. So please see, and since this end point was B1 dash, so this will become B2. Had I marked it B2 dash, this would have become B1. That is the only change. Now you see, it may seem to be complicated that these views, they are intersecting with each other. No, it's not complicated. I know one very simple fact. That simple fact is I have my true length over here. So I need to obtain the apparent length in the opposite view, which will be parallel to either HP or either it will be parallel to VP. So just see, I will be just inverting these arrows. So first I'll draw from the second point of this true length perpendicular line to the first point locus line of the opposite view. Just see, from here I'll draw one vertical line so that my opposite view projection becomes parallel to HP over here, and then rotate it back to obtain the projection in the front view. Similarly over here, this was my true length in the elevation. From here I'll drop a perpendicular so that the opposite view projection becomes parallel to vertical plane. Now over here, once I get my projection parallel to VP, then my true length in elevation will be obtained. And once I do this, then I will rotate it, just reverse the arrow, obtain the point B. If this B dash and B, they fall in one line, my problem is solved. So let us start the same thing over here. Please see, from here I have to start. So B1 dash is my first point. So this is the, please check, true length in elevation. So from the true length in elevation, I will be dropping a perpendicular onto the plan side. Please see, I will be dropping a perpendicular over here. You can see once again, this is my B2 dash. From here I am going to drop a perpendicular onto the plan side, that is at the locus of A, first point of my opposite view. Once I drop a perpendicular here, my apparent length will become parallel to the vertical plane. So please check, this is my elevation true length. I want to obtain my apparent length in the plan such a way that it is parallel to VP. You see, by dropping this perpendicular from B1 dash to the locus of A, that is opposite side first point, I have ensured that AB1, which is my apparent length, this is parallel to the vertical plane. Please check this out. This is parallel to the vertical plane. Over here, this was parallel to the vertical plane. Then what I need to do, keep my needle here, rotate it back to the second point of the true length of the plan. I will get my apparent length projection point B. So from here, again you see, I'll keep my needle here, open compass this much, and now I will be rotating it to this locus line B2. I will be rotating it back to the locus line of the plan, which is B2, true length of the plan. So please see, I am going to rotate it back till I intersect this particular line, projection line of the true length of the plan. Same thing I did over here. Now I have obtained point B. Having obtained this point B, I am going to join A with B. So once I join A with B, I can mark this angle as beta. I can mark this angle as beta. Similarly, now the second proposition over here, true length in the plan is available. So true length in the plan will be possible when my apparent length in elevation is parallel to the horizontal plane. Please see, I drop a perpendicular from the second point of the plan. Over here you see, I drop a perpendicular from the second point of the plan, that is true length of the plan, to first point locus line of the elevation. Why? Because only then my elevation apparent length will become parallel to the horizontal plane. Whenever my elevation side apparent length becomes parallel to the horizontal plane, my true length will be obtained in vertical plane on the horizontal plane. So my true length is already available. Since my true length is available, this will become true length only when my elevation apparent length is parallel to HP. So please see, I have dropped a perpendicular up to the locus line of elevation first point A dash. So once I do that, please see, this is my apparent length A dash B2 dash. So this is parallel to HP. So this I have already obtained. Now I'll keep the needle of my compass here, open this much, rotate it back up to the second point, that is the true length of the elevation. So true length of the elevation locus line is this one. Please check this out. It is this one, red one. So I am going to rotate it back till I reach here. And once I obtain this, name of this point will be B dash. And I have made appropriate extensions and rotations if I get the B and B dash point lying in one vertical line over here. Similarly, B dash and B, if they fall in one vertical line, this is the self check which I have applied. So since over here as well, B dash and B, they are falling in one vertical line. So now confidently I am going to join A dash and B dash over here. So this is my elevation projection line, and its inclination with HP will be indicated by angle alpha. This angle will be angle theta. Here, this angle, it is angle beta over here, and this angle over here, this is my angle phi. So please see, let us mark the angles over here and let us work out the traces. So you see, wherever, again, I don't need to carry out these extensions over here because the lines, they are themselves intersecting. And which lines I have to focus over here? The blue lines, because A dash B dash blue line, it is the elevation apparent length. A B blue line, this is my plan apparent length. Now please check, wherever my elevation apparent length A dash B dash, it intersects the XY line, I get the point H dash over here. So from this H dash, I'll draw vertical perpendicular up or down till it meets my plan projection line of AB. So from here, I'll get H dash, I'll extend it vertically downwards to meet this plan projection line, I'll get point H over here. Similarly, my plan projection line AB, it intersects with XY line over here. This gives me point V, and then I drop a perpendicular onto the elevation projection line A dash B dash. So wherever it intersects with over here, this will give me point V dash. So let us mark these traces. Just see, this is H dash. As I explained to you earlier, this point will be H, this point will be my V, and this point over here vertically perpendicular will be my V dash. So measure this length H dash H, measure this length V dash. So this will give you horizontal trace measure, and this distance will give you the measure of the vertical trace. So through this you can work out all these angles alpha, beta, theta, phi. And one thing you need to remember, this is very important, true length is never rotated, its horizontal component is evaluated and it is further rotated to locate the apparent views and the angles of alpha beta. So this particular concept you need to remember to evaluate the projections for the oblique line, which may lie in any quadrant over there for that matter. So this is about the projections of the oblique lines. Now we are going to discuss further few more cases, that is the case 3, in which the partial projections will be provided to you and you will be provided information regarding horizontal trace and the vertical trace, and using this partial information of the projections and the information regarding traces, again we are required to work out the projections as well as the true lengths of the line and the traces of the line. But that part we are going to pick up in our next lecture, and this is all for today. So I hope through this deliberations you have been able to understand the projections of the oblique lines for the cases in which first point lies in quadrant number 1 and the second point happens to lie in quadrant number 3. So thank you very much. Thanks a lot.